Yeah, Manuel, you turned off the lights. Perfect. Okay. Yes, I'm happy to be here. This is the third time I've given a lecture here. I gave last year and the year before, and it's always great. And of course, this is about Einstein and the story of 1905, which was truly his incredible year. My name is Don Ellison. I'm retired from the Department of Physics, North Carolina State University in Raleigh, North Carolina. And here is Einstein in 1905 at the patent office. So that's part of our story. First of all, yes, if you have a question, just yell out or raise your hand, and I try to answer questions as we go along. And I will, if you send me an email, I will email my slides if requested. I have a lot of links that you might be interested in that you can get from those. Okay, so, and there's another thing. Einstein was literally the most famous scientist in the world for decades, so there are hundreds of biographies about him. This is a very good one by Walter Isaacson. And I have used this, wherever you see a quote in my talks, it comes from Isaacson's book. Okay, so in 1905, Albert Einstein published 5 scientific papers that literally changed how we view the world. I mean, there's no exaggeration there. He was 26 years old, working as a patent clerk, third class, in Bern, Switzerland. And here he is in 1905. Here's Bern, Switzerland there. So this is the story, you know. One of the 5 papers basically introduced quantum physics. It was the beginning of quantum physics, which is one of the great scientific developments in the 20th century. And 2 papers described the theory of special relativity, the theory that he's most famous for. Here he is in 1912, a nice-looking guy. So this is the question. This is what we have to somehow answer. How did Einstein, perhaps the greatest scientist ever, end up working in Bern, Switzerland as a third-class patent clerk? Here he is with his sister. Here they are later in life, and they remained close after they both came to the U.S. in the 30s. Okay, Einstein was born in Germany in 1879. A year after he was born, the family moved to Munich, and his father and uncle opened an electrical supply company. And this is important because they were both engineers, so they were well-educated, technical people. And the Einstein Brothers company was at the forefront of electrification of cities, which was new then. Cities were getting electric lights for the first time ever. So they were building the equipment and electrifying cities. And actually, they were the first to provide lights for Munich's Oktoberfest in 1885. So he came from an intelligent, intellectual family. But by nature, he resisted authority. He was a free thinker, for sure. And he found German schools, even in Munich, he found them very oppressive. The military tone, the Prussian glorification of the military. When Einstein was 15, his father's company failed. Apparently, his father was not the greatest business person in the world. And the family moved to Italy, and they left Albert with relatives in Munich to finish his last 3 years of high school. Well, that didn't last very long. Albert soon left school, joined his parents in Italy, and declared he was never going back to Germany. He would study on his own. Just couldn't stand the German mentality. He renounced his German citizenship 1896 at age 17 and was stateless for 4 years before becoming a Swiss citizen. And he was very proud of the fact that he was a Swiss citizen. However, once he became famous in 1914, he did accept a position at the Prussian Academy of Sciences in Berlin, which was the premier physics position in the world. He didn't turn that down, but under the condition that he had dual citizenship. Okay, so the bottom line for his education, he was obviously exceptional from an early age. He had some trouble learning to speak, but it was just some kind of condition that he got over. He was self-taught in physics and math, well beyond his classmates. He wrote his first scientific paper at age 16 on the ether, and we'll talk about that, this idea that space was filled with this medium that allowed light to move through it. And this was the start of his obsession with the nature of light. And the nature of light really is very important for the development of relativity and some of the other work that he did in 1905. So we're going to be talking a lot about light. Here's Bern, Switzerland. So we want to know how he got there. I come from North Carolina, Raleigh, North Carolina, and on the coast of North Carolina is a nice little town called New Bern. And it's named after Bern, and of course Bern means bear. And in Bern, Switzerland, I've been there quite a number of times, they actually have a bear pit here, where they have a live bear. At least the last time I was there, they had some bears. It was a nice bear pit, no problem. In New Bern, North Carolina, we have real bears. We have wild bears. And our friend of ours has a bear that robs her bird feeders every so often. So anyway, okay. So, well, first we start in Zurich. He entered Zurich Polytechnic University at age 17. He failed the exit exam a year earlier because he had trouble with his French. This is Switzerland, and he didn't do too well. This was not the best university in Zurich. It was the second best because of his bad high school grades and so on. He couldn't get into the best university. He got into Zurich Polytechnic. Zurich Polytechnic had two physics professors, Heinrich Weber and Jean Pernet. 11 students in Einstein's freshman class. 11 students, two physics professors. Okay. Einstein soon pissed off both of them. He called Professor Weber Herr Weber instead of Herr Professor Weber. And if you know anything about the Germans, that's an important thing for them. Okay. He complains that Weber was not teaching the latest physics. Okay. As far as Pernet taught the laboratory classes, and in 1899, Einstein caused an explosion in the lab, injured his hand, and he couldn't write or play the violin for some weeks. So obviously he didn't do too well with the second professor. And by all accounts, Einstein was quite a good violinist. And he was good. Zurich Polytechnic also had a very famous math professor, Hermann Minkowski. If you studied math at all, you've certainly heard the name Minkowski. It's very famous. Einstein avoided his difficult classes. He just didn't go to his classes. And later, Minkowski labeled Einstein a lazy dog who never bothered about math at all. Unfortunately, Minkowski died young from appendicitis at 44. In 1908, a year before he died, he showed, now Einstein has published his work on relativity, he showed that Einstein's relativity could be expressed in four-dimensional space-time. This was very important. It was a technical mathematical thing that Einstein didn't come up with right away. 3 dimensions of space and 1 dimension of time are joined. And they actually talked at that later time, and it's certain that Einstein and Minkowski would have become collaborators if he had lived. And it would have been important for Einstein because Minkowski knew the math that Einstein didn't know. Okay. One of his classmates was Marcel Grossmann. He was a good mathematician, and Einstein used his math notes to study for exams because he didn't go to class. And Grossmann became an expert in tensor calculus and non-Euclidean geometry, and these forms of mathematics became essential for general relativity, Einstein's later work where he came up with a new theory of gravity. Very, very difficult, very, very complicated. And they remained friends and collaborated for the rest of their lives, Grossmann and Einstein. Okay. Also in the class was Mileva Marek, and she would become Einstein's first wife. Okay. And Mileva Marek was characterized as smart, intellectual, dark, and intense. She was not well liked by Einstein's family or friends. Einstein's father would not give his consent for him to marry her until on his deathbed, before he would give consent. Einstein certainly liked her. She was intelligent. She was a physics major in college, so he could talk to her about his work. She was from a wealthy Serbian family, strongly encouraged to study science and math by her father. She was certainly exceptional, but she was not unique. Apparently, she was not the first woman to study physics at Zurich Polytechnic. Okay. And of course, I'm saying this because there's been a controversy now for some time about concerning the role that Mileva played in Einstein's work. And they certainly worked together some. They were students together. But as far as I can see, there's no evidence that she contributed significantly to relativity ideas. And the reason for this is that his ideas were so far beyond what people were thinking. He communicated with the top physicists in the world. They didn't know they were writing letters back and forth to a patent clerk at the time. And this was not something that, and most of those top scientists didn't think there was anything to relativity. It was so far out. Okay. But of course, they became romantically involved. They studied together some, but lived separately. They're both strong-willed and very independent people. They worked together on the senior research paper. They take final exams in 1900. Einstein passed at the bottom of his class, but he did pass. Okay? Einstein was the only person who graduated not offered a teaching position at Zurich Polytechnic. And he attributed this to Herr Weber, who just, you know. Merrick did not graduate. He failed the exam. Okay. So now Einstein has he graduated. He starts looking for an academic job. He starts applying all over Europe. No offers. Oftentimes, they never even replied to his application. He actually, at some point, he sent self-addressed return postcards. These were never returned. Some of these have ended up in museums, you know, they now have Einstein's postcard. He goes 2 years without finding a permanent job. 2 years. Okay. In 1901, Albert and Maliva meet at Lake Como. They spend time together, and Maliva gets pregnant. Okay, in 1901. And this is really quite amazing. A baby girl, Lysero, I think is how you pronounce it, was born in January 1902. Maliva was with parents in Serbia, and Einstein was in Bern, trying to get his job. It's unclear what happened to this child. And this is the amazing thing. She was unknown to Einstein scholars until 1986. Einstein literally was the most important scientist in the world for decades. Decades. Everybody who even met him, you know, they were interviewed and say, oh, what can you tell me about Albert Einstein 20 years ago? Nobody knew about this until a couple of letters mentioning her were released. It's clear that neither Einstein nor Maliva wanted to talk about this. It's unlikely that Einstein ever saw the child. It's not clear he ever mentioned the child to his parents. No mention in later letters. Most likely she died as an infant, but we don't know. She could have been given up for adoption. Okay, but in any case, Maliva getting pregnant focused Albert's attention on finding a permanent job. He's convinced that Weber is sabotaging his search for an academic job, so he expands his search and taps his personal connections. Fortunately, he has personal connections. Marcel Grossman has connections, okay, one of his classmates. So Grossman sets up Einstein for a job at the patent office in Bern. So that's how he ends up in Bern. You know, he gets this job. So Einstein's in Bern waiting for a job to start when Lysera is born in Serbia. Maliva and Albert are married in Bern in January 1903. Lysera is never brought to Bern. They have a son, Hans Albert, which is born in 1904, and here he is with his son, Hans Albert. January 1903 was the first time Albert and Maliva have ever lived together. Before that, they were writing letters back and forth, living separately, and so on. And here's Bern. This is a beautiful city. I don't know if anybody's been there. I've been there a number of times because there are scientific reasons for going there. This is where they lived, right there, 49 Kamgasse. And of course, this is Switzerland, so Bern was never bombed, so it's still a nice medieval city. Here's their second floor apartment. It looks really nice now. I'm sure it wasn't so nice in 1903, 1905. That's where they lived, and you can go there. It's a nice little museum. Every time I go to Bern, I go at the apartment. I just assume that waves are going to sink in or something, you know, but it hasn't happened yet. So here's the apartment right here, and here's the famous clock tower. And the old patent office apparently was behind the clock tower. It's not there anymore. But you have to imagine every morning Einstein walking to work from his apartment to the patent office, seeing this clock tower. And time becomes very, very important in relativity. It's an essential thing that comes up. So every day he walked and saw the hands of the clock moving and thinking about time. You know, you have to imagine that. You know. Here's the patent office during his time. It actually was not a bad job for Einstein. It paid more than an assistant professor. And many patents concerned electricity and magnetism, which were relatively new then. That's going to be important for him. And how to synchronize clocks. Railroads were just coming into being in Europe then, being developed. And so if you have railroads, you have to have timetables. And if you have timetables, you have to have synchronized clocks. And so there are a lot of important ideas, a lot of patents concerning these things. But, of course, Einstein's a pretty smart guy. He could do the required work in 2 or 3 hours, work on his own work the rest of the time. Apparently he had little pieces of paper that he did his stuff and then hid them when his boss came by. But that's the story. The bottom line, he was a pretty good patent clerk, is the bottom line. But this is a full-time job, 6 days a week. With a full-time job, a wife and baby, little access to frontline physics. He's in Bern, working in a patent office, and remotely working on a PhD thesis with an advisor in Zurich. There was no university in Bern that gave a PhD. He produced perhaps the most original body of work of any scientist before or since. Absolutely incredible. So now we have to talk a little bit about what he actually did. Here are his 5 papers that he published. And some of course, he didn't do all these in 1 year. He had been thinking about these, obsessed with these ideas for a decade, since he was 15. Okay. Here he published the dates: June, July, September. Apparently, after he finished, he slept for 2 weeks. I mean, this is absolutely amazing. And here's an excellent article, some math in it. Okay, the first 3 papers here connect the invisible microscopic world of atoms and photons with the macroscopic world, the large-scale world, the laboratory world that can be measured, connecting the microscopic to the macroscopic. These were mainly talking about physics that was going on then. They had immediate practical applications for Einstein's work. The last 2 on relativity were the discovery of relativity, a new view of physical reality, a new view of reality. That's a pretty strong statement. No practical applications for years for these papers. Okay. Oh, this one, by the way, you can see published 1 day later, and it's just, I'll show that paper at the end. Okay, let's go through this a little bit. Start with the PhD thesis on the size of molecules. And he had to get his PhD in the University of Zurich because they offered a PhD. Okay. Oh, do we have a question? No, we don't. Okay. So a new determination of molecular dimensions. This was his most conventional topic. And he knew that if he submitted relativity for his PhD thesis, it would have been rejected immediately outright because it was so ridiculous at the time. And again, he needed a PhD to get promoted to patent clerk 2nd class. That's why otherwise he did not need it for his work. He did not need a PhD for his work at all, only he was supporting a family and so on. But this PhD work is important. It was an important part of the development of statistical mechanics. That's an area of physics where you investigate large numbers of atoms and so on using statistics. It's used every day in physics today. Very, very important. And with this thesis, he obtained a new value of Avogadro's number. You all learned about that in school. And determined the size of sugar molecules using this. Pardon?
Can you explain Avogadro's?
Avogadro's number is the, Avogadro's number is the number of atoms in a mole. Then you have to ask, well, what's a mole? A mole is a certain specific number of atoms for an element. Like you have carbon. Carbon has 6 protons and 6 neutrons, that's 12. So if you take 12 grams of carbon, it has a certain number of atoms, Avogadro's number. If you have oxygen, oxygen has 8 protons, 8 neutrons, that's 16. If you take 16 grams of oxygen, it has the same number of molecules as 12 grams of carbon. That's probably more than you need to know about that. But it's an important number that relates a macroscopic thing that we can measure, the grams of a substance, the number of atoms that are there. We can't see atoms. Okay, and in fact, in 1905, it was not universally accepted that atoms exist. That's the important thing here, okay? This was a complicated calculation at the cutting edge of statistical thermodynamics. Again, it's another branch of physics that is used every day today. So he was doing important physics with his PhD thesis. He started his PhD with Professor Weber. We had trouble with him already. He had to switch to Kleiner, Alfred Kleiner, in 1901. Here, he almost gave up in 1902. You know, I don't know how many people here have gotten a PhD or had students, whatever. They start, oh, you have to have a certain number of spaces, and the biography has to be done in a certain way. Einstein could not stand that. But he stuck with it, and he finally got his PhD in 1906. Okay, the second paper that he did, Brownian motion. Brownian motion, it comes about because it was known that pollen, little pieces of stuff in water or some other substance, was seen to jiggle around. Okay, that's something. Scientists worry about stuff like this. Okay, microscopes could see the pollen, but they, of course, could not see the water molecules. So you have something which is kind of jiggling around. What caused the pollen to move? Again, this is scientists worry about stuff like this. So you have a grain of pollen surrounded by unseen water molecules. As time goes on, the pollen wanders away from the starting point. Okay? Well, what Einstein did is he said, okay, let's see if we can figure out what's going on. He assumed that the pollen was being constantly hit by water molecules, even though you couldn't see them. It was constantly hitting them randomly. And if it hits them randomly, they will actually move. And he predicted how far the pollen moved versus time, using these statistical methods, all these different molecules. And it turns out that the distance they move over a certain time depends precisely on the size of the atoms. Precisely on the size of the atoms. This is something that can be measured. Okay? And in fact, Jean Perrin confirmed Einstein's predictions in 1908. He did this in 1905. This basically was proof for the existence of atoms. I mean, think about that in 1908. Because now you have a precise prediction that depends on there being atoms there. You can measure it in the laboratory, and there it is. And I find it interesting that Perrin got the Nobel Prize in 1926. In part, it was given to him for confirming Einstein's prediction. Okay. Photoelectric effect. Now, this is one of the important ones. Okay. Einstein considered this to be the most revolutionary, and in many ways, it was at the time. In 1905, and this gets a little complicated now, in 1905, every scientist believed that light was a wave. Light was a wave. Light as a wave of oscillating electric and magnetic fields. That was, and this was, there had been a lot of theory developed by James Clerk Maxwell in the decades before that really, there was other reasons, experimental reasons why everybody believed that light was a wave. So light as a wave of oscillating electric and magnetic fields, okay? And light moves at a speed of 186,000 miles per second in a vacuum. That was known then, that there's a very high speed. So all evidence in 1905 suggested that light was a wave. Okay. And since waves need a medium to move through, all scientists in 1905 believed that light moves through a vacuum. They believe that a vacuum must be filled with something for light to move through. Sound waves move through air, water waves move through water, seismic waves move through rock. There had to be something for these light waves to move through, and they called this medium, they called it the ether. Okay? And everybody believed it must be there. Also in 1905, experiments were being done on the photoelectric effect. So now we have this whole body of work leading up to 1905 telling us that light is a wave. Okay? And this is a photoelectric effect. If you have light, if you shine light on a metal surface, it can cause electrons to jump off the surface. Okay? And this was being measured. It's a difficult experiment. It was a difficult experiment to do in 1905. So the electrons in the metal absorb energy from light and jump from the surface. The problem is that the experiments measured how the electrons jump from the surface, and it was found that the electrons were emitted. They jumped from the surface in a way that was not possible if light is a wave. Okay, well, here we have an experiment that can't be understood, assuming light is a wave. Einstein said, okay, well, I can explain that experiment by assuming that light is made up of packets of energy called photons. This was a radically new, different idea, that light was made up of packets of energy, not a smooth wave spreading out. And the electrons absorb a photon, all or nothing. So the light will come in, there's a packet of energy, electron can absorb the entire packet and jump off. So these photons are quanta of energy. This is the beginning of quantum physics here. Okay. And this was truly a radical idea. There was no doubt leading up to that light could act as a wave, and it can. You can do an experiment that light acts exactly like a wave. Einstein's explanation for a photoelectric effect showed that there was no doubt that light could act just like a particle. So, and this was the first hint of the wave-particle duality. Light can act like a wave, or it can act like a particle. What you measure depends on what experiment you do. Okay, it has this dual nature. We now know that this applies across. It applies to not only light, but it applies to particles, electrons, everything. It's a fundamental basis for quantum physics, wave-particle duality. Okay, so we have two seemingly contradictory ways to describe light: as a continuous waves of energy moving at speed c, or as a gazillion little photons of discrete packets of energy all moving at c. It turns out that waves, the idea of a wave is an approximation. Photons are the correct way, the more correct way to describe light. Okay? Everybody here has a cell phone, I guarantee. The CCDs in your cell phone and digital camera use the photoelectric effect. The same effect that Einstein explained in 1905. There's a few embellishments in the last 100 years or so. Your cell phone only works because photons are real. So there's no doubt that they're real. And the CCDs. Another nice application is the human eye. The human eye only works because light is made up of photons. The cells in the human eye, the rods and the cones, they detect photons, not waves of light. So, okay. So, wave-particle duality. Sometimes light acts like a wave, sometimes light acts just like a particle. What this is telling us is that light was very strange. And it was just, how can it be at that time? And of course, Einstein's been worrying about light since he was 15, because there are reasons to think that light was bizarre even before this came up with Maxwell's equations and so on, which I'm not going to talk about. So, the last two papers on special relativity are concerned with the nature of light, basically. Starts off with the nature of light, the special theory of relativity. This was published one day after this one. It's just an addendum. Okay. So again, in 1900, 1905, everybody believed light required something to move through. Sound waves needed air, water waves needed water. Light, as a wave, should have a medium to move through, and this medium was called the ether. Actually, it had a fancier name, the luminiferous ether, if you say that 3 times rapidly. Okay, so the speed of light, always called c, was measured and known to be 186,000 miles per second in a vacuum. Okay. Now, let's think about waves a little bit. Now, Einstein is switching back to thinking about light as a wave. He had just said, okay, light can be photons, but now he's thinking of it as a wave. And it works, his relativity works for either way. A surface wave, you drop a stone in a pond, and you have the waves moving out. The speed of the wave is determined by the properties of the water, okay, as it moved out, the density of the water and so on, okay? All scientists in 1905 expected light to act the same way moving through the ether. Light is moving through the ether determines the speed of light, 186,000 miles per second. Well, if you have a boat that's moving slowly through the water, it produces a wave, a water wave. The speed of the wave does not depend on the speed of the source, the speed of the boat, okay? the speed of the boat doesn't matter. You see how that works? If it's moving slowly, it produces a wave in front of the boat, and that wave moves out through the water. Okay. That's how normal waves work. Okay? So the speed is determined by the properties of the water. Here's a boat producing a wave. If you have a stationary boat measuring the speed of this wave, it will measure a certain speed as it goes by. If you have a boat that's moving through the water, measuring the speed of that wave, it will measure a different, in this case, a faster speed for the water wave. Does everybody see how that would work with water? Okay? If you have a wave going through the water and you're going through a boat and you measure the speed of that wave, you're going to measure a faster speed. If light acted like sound waves, which everybody expected, the measured speed of light should depend on the speed of the ether, or how fast you were moving through the ether. This had to be the case. Okay. So, well, the ether has to fill all space. We have light coming from distant stars. That light, if this idea is correct, must be moving through the ether. As the Earth goes around the sun, it's moving through the ether, just like the boat's moving through the water. It's going to measure a different speed of light coming from the stars. This was the idea. So the measured speed of light coming from the stars should change during the year as the Earth is moving through the ether. Seeing a difference, if you can measure that, it would prove that the ether existed. Okay. Well, a lot of experiments tried to do this. Many careful experiments. Finally, Michelson and Morley, two Americans, did a very good experiment in 1887, and they didn't find an ether. They did a really good experiment, and there was no ether there, no measurement of an ether. Okay? So, most scientists at the time said, well, obviously the ether is there. We have to explain why this experiment got a null result. There must be some other reason. Einstein did a little bit differently. So this result suggested that the speed of light was independent of the speed of the source. This is the normal thing. The boat moving through the water produces a wave, and that speed of that wave doesn't care about how fast the boat's moving. Okay? That's just like sound waves. But now we see that the speed of light is independent of the speed of the observer. This is not like sound waves. This is very different from sound waves. Okay. So, stationary boat measures one speed, boat moving through measures a faster speed. For light, the speed does not depend on the speed of the observer. So if this was light, both of these boats would measure the same speed, moving or not. And this is very different. Very different. And this was the clue that Einstein needed. Waves are an approximation. Photons are a more correct way to describe light, but relativity applies equally well whether you consider light a wave or photons. Okay. Now, Einstein guessed that light was somehow fundamentally special in the universe. Okay, he was 26 years old, working as a patent clerk. He had nothing to lose, basically. So, okay. And plus, he was a genius. Okay. He accepted that the ether did not exist. Okay? He guessed that the speed of light was always c, regardless of the source or the observer. This is the critical thing. Light will slow down going through glass or air, but that's something else. That's index of refraction. Forget about that. The point is that the speed of light is always c, regardless of the source or the observer. Okay. So, this extraordinary nature, this strange thing about light, change was a clue that there's something about reality that we don't understand. And the key lies in how you measure time. So here it goes back to time, and every morning Einstein walking past the big clock in his town thinking about time. So the question, what's the best possible clock? This is a nice one. You pick up this Rolex for $600,000, that's US dollars. It's pre-owned, of course, but this is nice, but it's not the best possible clock. Okay? The best possible clock is based on light, because light is fundamental. So we have to have a clock that's based on light. So here's the best possible clock. You have two mirrors. light post bounces back and forth. Every time it hits the mirror, you have the tick of the clock. Tick, 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 tick. That's a clock. Okay, now imagine, here's where it gets a little difficult. Imagine you're a stationary observer. Here's your stationary clock, and you observe an identical clock moving past you. Okay? You observe that. So you see the light bouncing up and down in that identical clock, moving past you. Okay. Now, the distance that light travels, as you see, is greater here than it is here. Right? Because it's moving past you. You see it doing that as the clock goes past. If light always has speed c, if the speed is always c, doesn't change, each tick is longer because the light has farther to go. The ticks are going to be longer. The faster the clock moves, the slower time runs. The faster the clock moves, the slower time runs. How fast time moves depends on speed. Okay? Now, this is very different from what would happen for sound waves or for a bouncing ball. Imagine a bouncing ball bouncing between two walls. Okay? So you see a ball bouncing up and down. You know, forget about friction or anything like that. If you see that ball moving, what you see is the speed of the ball going up and down, but you also see the speed of the ball going to the right. That's what you would normally expect. As seen by the stationary observer, it moves to the right as well as up and down. The total speed of the ball is seen to be greater than in a stationary clock because they're the up and down speed plus the lateral speed. Speed of the ball is seen to be greater. Okay? So, as seen by the stationary observer, the ball has farther to go, but it's moving faster. So the ticks of the two clocks are the same. This is absolute time. This is what everybody assumed was the case, that time was absolute. It didn't matter how fast you're going, your watch ticked at the same rate. Einstein said, no, it's not so clear. Okay, so here's the example. With light, speed is always c. So it has further to go, but the speed is always c, so it ticks more slowly. Time is relative to speed. With a ball, with a normal object, it clicks at the same rate, time is absolute. So these are the two cases, absolute time or relative time. Does this tell us that time is actually slowing down? The answer is absolutely yes. Time slows down. Time is relative to motion. There's no doubt about that. It's been proven thousands of times in the laboratory. Einstein, when he saw this, he saw that the strange nature opened a door to this hidden space-time reality. Space and time are not absolute. This is what this is telling us. But there was one more monumental leap, as I say, before he could go on. One more thing was required for this. Einstein proposed that the speed of light c was the ultimate speed limit, that nothing can move through space faster than c. Now, you may say, well, this is crazy. Why should there be an ultimate speed limit? But my question is, what's crazier, a speed limit or no speed limit? Imagine no speed limit. That means things can go at infinite speed. With no limit, you lose causality. It's crazier not to have a speed limit. The thing that is a mystery, certainly at this point, is why is it this particular speed that's the maximum speed limit? And that came out of Maxwell's equations, and this was a guess by Einstein. Had to be a guess, of course. It turns out he was right. Okay. Okay. Slowing of time is called time dilation. Moving clocks run slower. This is absolutely a real effect. Thousands of experiments have showed that. Nobody noticed this before Einstein because it's extremely small for normal speeds. Extremely small. The fastest any human being has ever gone is 25,000 miles per hour when the Apollo astronauts went to the moon. The fastest anybody has ever gone. If you traveled at that speed, 25,000 miles, for 1,000 years, you would age 22 seconds less than if you stayed home. Okay? So that's why it was never noticed. Nobody ever noticed that. In fact, it took years before they could do experiments that really demonstrated it. Okay, well, what about space? That was time. Well, if you want to measure the length of something, you have to use a clock. There's no way to avoid that. If you want to measure the length of something that's moving, length of a moving object, you have to use a clock. If you use the best possible clock, you find that moving objects become shorter. So length contracts. So if I have this little pointer here, when I'm moving here, and you measure the length, it will measure shorter than if you measure it when it's stationary. Again, it's a tiny, tiny, tiny effect. But they're real. How fast time runs is relative to how fast something moves. Okay, so how did Einstein come up with this? Well, he didn't start off, but he came up with the idea that we have these laws of physics. There's this great set of laws, Maxwell's equations for light. There were Newton's laws for mechanics and so on. And he said he believed that the laws of physics should be invariant. They should not depend on objects whether at rest or in motion. Well, if you assume that that's true, you find that Maxwell's equations for light are fine, but Newton's equations of motion, F equals ma, are not invariant. So you have to change one or the other, and Einstein changed Newton's laws. For this to be true, time and space are not absolute. They are relative to motion. Instead of time and space being absolute, Einstein believes the laws of physics should be absolute. And here, he started off calling his theory the theory of invariance, not the theory of relativity. And this, I think, would have made a tremendous amount of difference. Everybody think, theory of relativity, those physicists don't know what the hell they're doing, everything's relative. It's exactly the opposite. The laws of physics are invariant. They're not dependent on the frame of reference. Unfortunately, the most famous scientist in the world at the time, Max Planck, who he was communicating back and forth at the time, convinced Einstein to call it the theory of relativity in 1907. I think that was a big mistake. Minor, I guess, for Einstein. Okay, no questions yet. Okay, here we go. I'm almost finished, actually. So what happens to the rest of physics if you go from absolute time to relative time? Here's Newton, F equals ma, his laws of motion, force equals mass times Newton's laws assume absolute time and absolute space. It's built into them. Okay? Well, now Einstein's saying, well, no, I'm sorry. Time and space are not absolute. They're relative to speed. In 1904, nothing in science seemed more obvious than F equals ma. You all had seen that. This equation says, if you continue to apply a force to a mass, it will continue to accelerate. That's what it says. Well, if there is a speed limit, this must be wrong. Cannot be right. Something must be wrong with F equals ma. So this is what Einstein, 26-year-old, working in a patent office, saying, okay, you believe Newton for 200 years. He was wrong. So that's the point. Okay. But for F equals ma to have any meaning, you must be able to measure mass and motion. There's no getting around that. Okay? This requires a clock. If you use the best possible clock and you do some, make assumptions that conservation momentum still holds and so on, Einstein realized that a speed limit and time dilation, the fact that time is relative to motion, required changing the definition of mass. So now he's saying, well, you didn't really understand mass all these years. So you're talking about it. It's really a little bit different. Mass must depend on speed. The faster something moves, the more mass, the more inertia it has, the harder it becomes to push it. Okay. Einstein's new definition of mass. There is a rest mass. Rest mass is an intrinsic property of stuff. It's the mass something has when it is at rest. This mass is the mass of objects that are stationary. But when a mass moves at some speed v, the mass increases. If a mass is moving, its mass increases. Okay? As an equation here, don't worry about it. The faster a mass goes, the larger the mass becomes. As the speed approaches c, this maximum speed limit, the mass becomes so large you can't push it any faster. If you can see this equation here, you have the velocity that the mass is moving. This is the velocity of light. As v approaches c, this term approaches 1. Hopefully you can see that. You have 1 minus something which is getting close to 1. That's becoming very, very, very small. You're dividing by a very, very small number. The new mass becomes large. The faster it goes, the closer it gets to going at the speed c, the harder it is to push, and you simply can't push it faster than c. That's why it's the maximum speed limit. That's consistent with the maximum speed limit. This is his last paper. This is the entire paper. Okay? 3 pages. 3 pages long. I'm going to look at the 2 paragraphs near the end. Okay? Now, if you can read German, there you go. He changed the labels here, but paraphrasing. We are led to the more general conclusion that the mass of a body is a measure of its energy content. The mass is a measure of its energy content. If the energy changes by E, the mass changes in the same sense by E over c squared. If the mass, this is E equals mc squared. There's the equation right there. Only he used L and V. This m here is his new mass. It's this mass here, with this factor in it. The mass that increases the faster you go. Okay. E equals mc squared. As I said, this is I think the most famous equation in science. Everybody is. Why is this equation so special? Well, first of all, c, the speed of light is a constant. You square it, c times c, so it's an incredibly large number, c squared. But the speed of light is a constant. So the mass and the energy are, in a real sense, equivalent to each other, okay? Because of that constant factor. Moving masses had energy and motion. Everybody knew that. You had kinetic energy. Something's moving, it has a certain amount of kinetic energy. Now Einstein is saying there's a new energy, unknown energy, that's associated with mass alone. You imagine a cement truck moving down the road. It's really easy to imagine how much energy it has, kinetic energy. Einstein's new energy was hidden, is hidden. His new energy is hidden. Rest mass energy. For objects at rest, E equals m0 c squared is the rest mass energy. The energy that a mass at rest has. This new hidden energy is incredibly large, incredibly large. And the idea that there's this vast amount of hidden energy in mass was completely new. How large is it? The mass of a mosquito, 5 milligrams, has enough rest mass energy in those 5 milligrams to lift a cruise ship 725 feet in the air. Now you can imagine a mosquito flying around. It has a certain amount of kinetic energy. The rest mass energy associated with this mass alone is a gazillion times greater. Unbelievable. And this rest mass energy remained hidden from human understanding until Einstein corrected our erroneous ideas of space and time. So, where does this energy hide? That's the question. And I just started worrying about this a couple weeks ago because I've given this lecture before, and I basically, get to this, and I say everybody's heard of E equals mc squared. But then, of course, the question, it's hidden, but where is it hiding? That's what I'm going to try and talk about now. The problem is I don't understand it, so you take... if I didn't say that, you'd never would have known. But anyway. Okay, a little history. Electrons were discovered in 1897. Einstein did his great work, E equals mc squared, in 1905. Protons were not discovered in 1920. Neutrons were only discovered in 1933. That's less than 100 years ago. Well, All atoms are made up of protons, neutrons, and electrons. Here's carbon. We're made out of carbon atoms, along with a bunch of other stuff. 6 protons, 6 neutrons, and 6 electrons. So all normal matter is made of protons, neutrons, and electrons. Einstein's energy is hidden in the protons and neutrons. It's hidden in the protons. So when we first came up, discovered protons and neutrons, the first idea in 1933 basically was that protons and neutrons were little solid balls, solid little balls. Proton has a plus electric charge, neutrons have 0 electric charge. They have a certain amount of mass. They both have something called spin. We don't have to worry about that at all. Together, protons and neutrons are called nucleons, just makes it easier to talk about them. They're the stuff that nuclei are made out of, protons and neutrons. Well, in 1960s and 70s, we started building these accelerators, these atom smashers, to investigate what's going on. And it was discovered that protons and neutrons are not fundamental. They are made up of quarks and gluons. There are up quarks, down quarks, and gluons. Gluons, as the name implies, kind of act like glue that holds these quarks together inside the proton and neutron. Each, in addition to an electric charge, they have a different types of charge, which is called color. Again, very, very complicated, but this is not as bad as it gets. Protons and neutrons are not little solid balls. They're made up of smaller pieces. So imagine an onion. So now scientists are peeling away the layers of the onion, trying to figure out what's really going on, with what are protons really made out of. So the little solid balls is replaced by quarks and gluons. Well, in the 1980s, bigger accelerators were built, bigger atom smashers. The larger the accelerator, the smaller you can investigate, the smaller piece of stuff you can investigate. It was found that there aren't 2 or 3 big quarks inside of protons and neutrons. There are a whole bunch of little quarks and gluons, tiny quark-antiquark pairs. You have a quark and you have an antiquark, that's antimatter, and these are virtual particles. They pop in and out of existence. Okay, you think, see, now you can see that ether sounded strange, but this is even stranger, right? Pop in and out of existence. It turns out that nucleons are incredibly complicated and not fully understood today. They're not fully understood today because it's more complicated than this. You have all these little quarks, antiquarks, gluons flying away around inside the proton and neutron, and they're held together in something that looks like it's a solid ball by the gluons. This is that glue that's holding everything together, but they're flying around at very, very high speed. Something that's moving at high speed has a lot of energy, kinetic energy. The source of the rest mass energy mostly comes from the motion of the quark-antiquark pairs inside these particles. Most, not all. That's one of the things that people don't understand. So I started worrying about this now. And this is another diagram that we do not fully understand protons. We do not fully understand the most famous equation in science, equals MC. And people are, now if you hadn't known about this, this is something entirely new for you to worry about. You know, I mean, think about it. We don't know protons. How is that possible? Well, how do we figure it out? Well, that's why people build gigantic machines like the Large Hadron Collider and CERN to build these giant particle accelerators. The larger the machine, the smaller thing you can investigate. That's just the way it works. So you build these and you smash protons together, pieces fly out, these quark-antiquark pairs go to higher energy, something stranger even happens, and so on. And we still don't understand everything. It's amazing. Here's a guy on a bicycle inside this ring here. So, okay, I'm almost finished. So Einstein remained at the patent office until 1909. He continued working, published more papers, his reputation grew. In 1909, he gets a faculty position at University of Zurich, the university he couldn't go to because he wasn't good enough to get accepted at before. as with F equals ma, Newton's law, F equals ma, Einstein realized that Newton's law of gravity was also inconsistent with his ideas of invariance. Newton's law of gravity assumes absolute space and absolute time, okay? He became obsessed with finding a new law of gravity. From 1905 until 1915, 10 years, it took him to develop his theory of general relativity, which is a theory of gravity. And this theory is highly mathematical. It required all the hard math that he tried to avoid as a student, okay? But he didn't do this by himself. He was now famous. He was working in Germany. Germany at that time had the best mathematicians in the world, and he certainly learned from them. But he did this, there's no doubt, far more complicated. The equations of general relativity do obey his theory of invariance, general relativity, a new theory of gravity. In 1921, he gets the Nobel Prize for the photoelectric effect, not relativity. In 1921, there was still a lot of physicists that didn't swallow relativity. It was so strange, okay? Now, special relativity is beyond doubt. There's absolutely no question. You can't understand atoms without it or anything else. In 1962, quasars were discovered. Quasars are these objects that appeared to be extremely far away, but extremely bright. They were so far away that the fact that we could see them, that they were so bright. It became clear in 1962, 1963, that the only way you could power quasars was if you had massive black holes in the center of galaxies. And this was the first real astronomy application for general relativity, because this was not a star. This was not a star just making a lot of light. This required general relativity. It required a black hole. It required this new model of gravity. And now, of course, general relativity, Einstein's theory of gravity, is the only basis we have for understanding black holes and the expansion of the universe, cosmology, and so on. You can't do astrophysics without general relativity anymore. I mean, it's an essential tool. 75 years after he came up with this, the first real practical application of general relativity, the global positioning satellites, required general relativity for the accuracy. So this is a real-world application of general relativity. It only took 75 years for that. So that's it. Here are some of Einstein's friends and correspondents that he talked with in 1905. It's interesting that the only acknowledgement on his relativity paper is from his friend Michael Bessel, who is one of his patent clerk colleagues. Okay, that is it. Anybody have any questions? And actually, can we turn the lights on? Manuel, you here anywhere to turn the lights on? I guess not. Well, if you raise your hand, I can see. Yes.
Perspective is my undergraduate degree is political science. We call it soft science here.
Okay.
So as a practical matter, what did these accomplishments lead to that affect us to this day?
What does
these discoveries in 1905? How do they affect the history of the world after that? As a practical
well, you all have heard of Hiroshima, Nagasaki.
Right. I just want to confirm.
Yeah.
The right track.
Equals MC squared. But the global positioning satellite, it's 10% of the global economy depends on GPS or something like that.
But nonetheless, nuclear weapons are the big thing.
Yeah, unfortunately. Yeah. Well, you have nuclear power plants also. But in many ways, it's more than that. This is, that's saying, well, what does poetry contribute to our, economy?
Yeah.
Well, it does in very real sense, but it's not as obvious as some other things. Einstein's work, special relativity, you can't do chemistry without special relativity. So that's without doubt. But having this type of discovery, investigating the nature of atoms on a very, very fundamental level, protons, it's part of a scientific culture that is absolutely essential for all the other aspects of science and engineering. I mean, how many engineers kept studying math when they're 10 years old and 12 years old because they worried about cosmology. They had all these great images from James Webb Telescope and so on. If these things weren't there, the scientific culture would be a lot weaker. There's no doubt about that. Yeah, I think that's one way to say it.
Very good, thank you.
You wouldn't have the modern medicine you have today.
Oh yeah, well yeah, chemistry, everything depends on it. Yeah, quantum physics, of course, is, you know, your cell phones only work because of quantum physics. Everything only works because of quantum physics.
Aside from poetry, we could talk about Picasso's relationship to, is it Bocard, the mathematician Bocard? They had a close connection, and it was, it developed into concepts of fourth dimension, et cetera, and cubism, and immediately, you know.
Yeah, when the four-dimension really fed into art and literature very rapidly to a large degree. Yeah.
I think there are barriers to the knowledge
Now.
that won't be overcome until, as a species, we learn how to live together.
Yeah, it'd be nice to do that.
Because people who have the capacity to know where they can take us in terms of science know now where it's taken us so far, and they'll hold back.
Well, there's been a lot of negative aspects of science, that's for sure. I mean, and maybe I'll turn this off now. So, yes, you have to do these things sensibly. Einstein was a pacifist, for sure, most of his life. He did write the letter to Roosevelt, you know, prodding him to start working on the atomic bomb, but he was, yeah, it's a difficult thing.
It's
I don't
kind
know
of hard
what
to hear you from back,
Oh, you can't hear it?
back here.
Okay, I'm sorry, I turned it back on, hopefully you
Yeah,
can.
thank you.
Okay, yeah.
I want to ask about spooky action at a distance, and does that violate the law of speed of light invariance?
Yeah, the question is, you may have heard this, spooky action at a distance. Well, another word for this is entanglement, where you have, this is a quantum physics phenomena where two electrons, their particles can have wave properties, and their wave properties can be entangled together when you separate them. If you turn off one, the other one, you know instantly this is spooky. Einstein hated this. It's turned out to be correct. There's no doubt about it. It does not violate the maximum speed limit. You cannot send information faster than the speed of light with that. And but it's a real quantum mechanical effect. That's for sure. It's just the interpretation is misleading when to say that you can send information faster than the speed of light. Yeah. Did you have a question? No. Yes.
The absolute idea of speed of light.
Ah.
You can't possibly conceive of that altering in 150 years, like Newton's law did.
That's a good question. The question is, okay, yeah, you know, Newton's laws were assumed valid for 200 years or whatever, 150 years. Well, we know for certain that Einstein's theory of general relativity, his theory of gravity, is incomplete. We know that because it's inconsistent with quantum physics. So general relativity explains the universe on the largest scales. Quantum physics explains it on the smallest scales. But they're inconsistent with each other. So something has to change. So it has to be modified. So general relativity almost certainly would be modified. It's hard to imagine that one aspect of the speed of light being the maximum speed would go away or be modified because it's been confirmed so many times. But there will be modifications to Einstein's work. No doubt about that in the future. But they will be modest because you have thousands, tens of thousands of experiments that have been done and have produced results that are consistent with Einstein's theories. Now, if you change Einstein's theory, you don't change those experimental results. The new theory still has to explain those, okay? So it can't be a big change in what Einstein said, it has to be a small modification. Normally when you go into a new region, when you investigate something which is smaller or hotter or denser, then you can have an effect that you didn't know before. You can make a modification. But it's not going to be overthrown. And F equals ma is not overthrown. Every building, every bridge has been built assuming that F equals ma is correct. Because it's an approximation, it's an excellent approximation. And for all normal engineering things, it works perfectly. It's still taught in every physics classroom, F equals ma. But it's an approximation. And you have to know when that approximation is no longer valid.
I have another question.
Sure.
Did he ever make money off these brilliant theories that have contributed to the world?
Well, indirectly, of course. He didn't care much about money. He didn't. But, you know, he worked at the patent office. Apparently he had 50 patents. None of them made any money. He had one for some type of refrigerator, but which they tried to, he and a friend tried to, it didn't make any. But he didn't need a whole lot of money. Once he got famous, of course, he had all the money he needed. There's an interesting story. When he had to come to the United States, he left Germany in 1933. He was #1 on Hitler's hit list for assassination. So, but he got out. Of course, he was being offered positions at every university in the world, other than Germany, at the time. So he came to the United States and he went to Harvard and didn't like Harvard. So he ended up going to Princeton. They were setting up the Institute for Advanced Study at Princeton. It was just being set up then. And they wanted to hire Einstein. So the guy who was running it interviewed Einstein and he said, well, okay, how much money do you want to get paid? And at this time he's already had his second wife was now. And Einstein said, well, I don't know. I mean, I probably could get by with $3,000 a year, which is a fair amount of money. So the guy said, okay, I'm going to talk to Mrs. Einstein. So he goes talk to Mrs. Einstein, and they decide on $10,000 a year. but then the same guy hired this fancy mathematician who demanded like $12,000 a year. So the guy immediately gave Einstein $12,000 a year because you can't have that mathematician being paid more than Einstein. But now he didn't. Once he became famous, of course, he didn't need money. He could go anywhere. And, yes.
Why was he #1 on Hitler?
Oh, because he was Jewish. That's why. And they see Hitler and the Nazis did not like what they called Jewish physics. And relativity was Jewish physics. It was physics developed by Jews. And it was just horrible. I mean, it's a horrible thing. So, and of course, a lot of physicists in Germany were Jewish, and a lot of them got out, went to England. Many came to the United States. That's one reason why physics in the United States was jump-started by the Second World War. We had all these really great mathematicians and physicists coming out of Germany to the United States. Yeah. Yes?
This is from the Oppenheimer biography. There was Gödel, the mathematician, Gödel.
Gödel, yeah. Gödel, yeah.
And Oppenheimer said one of the greatest things he did was he knocked on Gödel's door at Princeton, and then he knocked on Einstein's door, and he said, I'd like you to meet one or the other. And they became friends and would walk around.
Yeah. Einstein ended up in Princeton. He was there until he died, and in the United States. You probably all saw the movie Oppenheimer. You all see that? Yeah. By that time, Einstein was not going to contribute to the Manhattan Project. He was beyond his prime in that. But, yeah.
Have you written any books yourself?
No books. No. There's too much work. Yeah. It is a lot of work, right? Yeah. No, I published a lot of papers. I did a lot of research. I was a professor. I taught, but mainly research. So I published a lot of. My main topic of main field was cosmic rays and particle acceleration. How do you accelerate particles in astrophysics, and, exploding stars, and so on. So I did that. But now I enjoy giving lectures. Yeah. And it's a lot easier when nobody in the audience really knows what I'm saying. You know? No, when you're giving it to experts, you have to be really careful. So,
It's on the test, I'm just kidding.
no, I mean, it's fine. No, I try not to say anything that's wrong, you know, which is not so easy sometimes. So you have to try to simplify things, make them understandable, avoid as much jargon as you can without oversimplifying it. And it's not so easy, but I try to not say anything that's wrong. And I do include a lot of those links if you want to get those. And then you can read the papers in a lot more detail in those. They're all on the web. You can find them pretty easily. Okay. Anything else? Okay. Well, thanks everyone for coming. Okay. Good.